Good morning, everyone. I want to quickly just go through a couple of the things that you're going to be watching today, but give it to you in more terms of notes so you're able to have a better context of how you're going to work on your worksheets later in the week and how you can apply it to the labs we're going to have. Okay, so the first thing we have of our two laws today is called Dalton's Law of Partial Pressures. And Dalton's Law of Partial Pressures states basically that if I have this Florence flask right here, and I would have different gases, so I have a red gas and a black and a blue gas, let's just say, and we could call those A, B, and C, that each gas creates its own pressure. Kind of like if you had three different books and you were holding the books in your arms. Each book would apply extra weight or pressure to the stack. So we could say the pressure or partial pressure of A plus the partial pressure of B plus the partial pressure of C. If you had further or more of those, you could keep adding those, but all of those together will be my total pressure. So how does that relate to what we're working on? Well, we're going to collect gas usually through water. So if I had some reaction down here and it bubbled through and oxygen was right on the top and I collected oxygen right here, sometimes you'd be asking a question that, what is the pressure of water? And you'd ask, well, why am I asking about the water? Well, all of us know that if it would rain or if water would be on the driveway or the sidewalk, that you wouldn't be shocked that later in the day the water would be gone. It would be evaporated. If it's evaporating, it's going from a liquid to a gas. So it's naturally going into a phase change. And that phase change creates gas, which has pressure. So every collection of gas through water will have a little bit of water vapor pressure as well. And that depends on the temperature. And we'll talk about that later. But if I were just to simply ask you, what is the pressure of my water? My container has oxygen and water. And what we're going to eventually learn is that these two equal the outside pressure. They're going to equal each other. So if I knew the atmospheric pressure, my atmospheric pressure is going to equal the pressure of my two gases inside the container. So looking at my information, I have my atmospheric pressure being 720 torr. I am telling you that my pressure of my oxygen is 100 or 705 torr. So what is my pressure of my water? Well, this really isn't all that complicated in terms of mathematical applications. I have 705 plus my pressure or my vapor pressure of my water, and it equals 720. So hopefully most of you would say, well, that sounds like it's 15 torr, right? 705 plus 15 equals 720. So that's going to be Dalton's law of partial pressures. You might have to take all the partial pressures and find the total. Sometimes you're going to have a total, and you're going to have to find one of the partial pressures. All right? The other law is a much bigger law, and this is huge. You're going to learn this in biology. You're going to use this in physics. This might be the most used gas law or chemical science equation at a intro level course used, period. It's called the ideal gas law. The whole point of an ideal gas law is being able to find a volume or a pressure or a temperature of a gas immediately. It's not like the pressure and volumes and temperatures that we learned before where it's P1V1 equals P2V2 because you need to have a before and an after. Like, this is my pressure and volume in the summer, what's now happening in the winter? That's too long of a waiting period. What is happening right now? So it is PV equals nRT. It's really important, and this is going to be utilized over and over again. So P is going to be pressure, V is volume. If we have a gas, it's important to know how much we have of it. So N is actually the moles of gas. I know that the letter doesn't match up, but we're out of letters in the alphabet. We only have 26 letters in the alphabet, and they've already used M for mass and other things. So that's that. R is going to be called a gas constant. We'll get into that later. And then T, hopefully you guessed, was temperature. Okay. The most important part of all this is actually understanding that the units really matter. Okay. So you have certain rules in this law that you didn't in our other laws. So for example, pressure. We can actually have different pressure units. That's why we made you learn about the 1 atm equals 101.3 kPa, which equals 760 torr, and so on and so forth. We'll come back to this. Volume has to be in liters. So if you have 1,000 milliliters, that's 1 liter. So if you have 950 milliliters, that's 0.95 liters. Moles of gas are moles. Gas constant is going to depend on what you use for your pressure. And temperature has to be in Kelvin. So reminder, that's adding 273. Okay. So for those of you that rearranging equations is a little tricky, if I want to solve for just P, this is what my new equation would be. I'm going to actually divide V under nRT. Okay. If I have solving for V, then it's nRT over P. If I'm solving for N, it's PV over RT. And if I'm solving for T, it's PV over NR. Okay. We will talk about the R value more, but I actually have a video for you that Tyler DeWitt actually goes over that. But I will tell you this, that if you are solving for R and you put PV over NT and you put in all the values of what the gas is doing, it will always equal the same number. It's crazy, but it will always equal the same number. Okay, so I want to talk about something else for today. So you'll recognize this, moles or mass, moles, particles, right? So we use molar mass here and Avogadro's number here. There's something really cool that happens. When a gas, when you have 1 mole of a gas at STP, so let's quickly review that. 1 mole, that's my N, right? And at STP, STP is 0 degrees Celsius and 1 atm. So if I put a 1 in, well here, right here, if I put a 1 for my moles, if I put 273 Kelvin, because 0 degrees Celsius plus 273 is 273, plus 1 atm, and if I put in a certain R value, when I multiply and divide that, it will always equal 22.4. So if I'm at STP, I can actually convert 1 mole to a volume using that number. So this will be molar mass, this will be Avogadro's number, and this will always be 22.4. So we take a look at your homework sheet for a moment. Now here's what I'm basically saying. If we look at your homework sheet for a minute, it says, what is the mass of 350 milliliters of nitrogen gas at STP? Okay, well, if we look at what we have is I want mass. So mass is up here, right? And I was told that I have milliliters. Well, milliliters is a volume. So I'm right there, okay? So now it's asking basically for you to convert milliliters to mass, but I'm at STP. So basically, you guys, is I can go 1 step, 2 steps. And that is going to look like this. So this one you could have converted already. You could have just put 0.35 liters, okay? If I have 0.35 liters, it's 1, 2 steps. So I'm going to take my 0.35 liters, divided by 22.4 liters, 1 mole. So now I'm in here. And then how do I get up to mass? By multiplying by the molar mass. So it'd be 0.35 divided by 22.4 times 28. So those are some of the things that you're going to utilize. Please watch the other 2 videos. It's going to be really helpful. And then you can start applying that to the worksheet that you are starting to learn. Reminder, 22.4 only works for STP. We'll talk about things when you're not at STP.